right, about time to get started here. So welcome to the inaugural episode of Datadog On, a new series from Datadog. My name is Jeremy. I'm the Director of Technical Community and Open Source here at Datadog. And I'm just going to start off by telling you a little bit about the series and then a little bit specifically about this episode. And then I'll leave it to my co-host here to kick things off and get started. So in the process of building a monitoring and analytics platform that ingests trillions of data points a day, Datadog has learned many lessons about scalability, about distributed systems, and specifically about distributed systems in the cloud. And we'd like to share those experiences with you, our community. So each episode will offer a conversation with the engineers who actually build Datadog. They'll share real-world experiences in architecting and building, operating, and monitoring modern systems, and give you actionable information that you can apply at your organization. And one core tenet here is that we're going to leave plenty of time for QA. So we really want this to be a discussion with everyone, not just with us. So do feel free to join in. There's a QA button there throughout the episode. As you have questions, put them there and we will answer them all at the end. And we've left, like I said, plenty of time to answer those questions. So do make sure that you jump in and join the discussion. Usually we're going to cover one topic per episode, but in this inaugural launch episode, we're going to cover two. The first one is going to start now. It's Datadog on Kafka, where Kirk is going to chat with Jamie, who's a senior software engineer, and Balthazar, who's the DRE team lead, two people responsible for building, scaling, and deploying Kafka here at Datadog. And as I mentioned, Datadog ingests trillions of data points a day, and Kafka is the messaging persistence layer underlying many of our highest traffic services. And consequently, as you can imagine, our Kafka usage is, to be blunt, quite high. We're talking, just to give you an idea of scale, double-digit gigabytes per second bandwidth and the need for petabytes of high-performance storage, even when we're talking about relatively short retention windows. So without further ado, Balthazar and Jamie are going to share their strategy in scaling Kafka, how we deploy it on Kubernetes, and they're also going to introduce you to kafka-kit, which is our open source toolkit for scaling Kafka clusters. Kirk, I'll leave it to you.
All right, so as Jeremy mentioned, we're going to take Q&A questions throughout, and we'll address them at the end. So I'm Kirk Kaiser. I'm a technical evangelist here at Datadog, and I'm the evangelism team lead. So today we're going to talk about scaling Kafka. And as Jeremy mentioned, Datadog is a monitoring and analytics platform that helps companies improve the observability of their infrastructure and applications. As he said, we have over 8,000 customers, millions of hosts, and we ingest trillions of data points per day. We do this using tens of Kafka clusters, and each one of those clusters can be running up to hundreds of instances. We're deployed on Kubernetes, at least partially, and we're multi-cloud. The way you see our Kubernetes usage, or Kafka usage on the front end is via things like this dashboard. We see events happening over a time period, and if you click in the top right window, you'll be able to see different time periods to filter through. So Kafka is one of the event processing systems that powers all of this. So Kafka itself is an event logging system. Typically, when we think of databases, we think of objects and things that happen to them. In Kafka, the model is a little bit different. First and foremost, it's a distributed system. We have a series of events that occur on a thing called a topic. It really gets interesting when you start subscribing to these topics and ingesting and mutating data on those events and republishing them back out. That's what powers the systems that do our sort of data ingestion and rolling up into time windows. As I said before, deploying Kafka is a little bit weird. If you're used to deploying a database like Postgres, MySQL, you're used to deploying just the software itself. With Kafka, you need a piece of software called Zookeeper. Zookeeper is your key value store, and it also includes a watch. Kafka itself elects the controller and stores the configuration values for the distributed system within Zookeeper. So let's talk a bit about the tooling used to scale these Kafka clusters. And for that, I'm going to introduce Jamie. Jamie?
Hey, how's it going? Jamie. I work on data platform team, mostly around tooling and scaling models and capacity planning and performance for Kafka. And so some of the tooling that we're about to talk about is kind of an iterative approach to starting small with some initial challenges we had around Kafka, and it's continued to evolve to cover some of our scaling challenges today. Yeah, so Kafka topics are essentially streaming distributed logs. And the breakdown for this, if you're not familiar, is that every topic is composed of partitions, and then every partition may or may not have partition replicas, and those replicas are spread over brokers. So for an example, we might have a topic called metrics, and partition 0 might live on brokers 1001, 1003, 1005, and so forth. And so for the metrics topic, we have two partitions described here. There might actually be closer to something like 64, 128, but this kind of gives you an example. If you're looking at P0, those 3 broker IDs in there represent the 3 replicas for partition 0. So if you were to see the full partition list for this topic, every single one of these partitions would have 3 replicas, and that represents a replication factor of 3. Yeah, so one of the reasons I initially created Topic Mapper is that out of the box, if you create a topic in Kafka, you'll know that it kind of just chooses to put partitions everywhere. And one of the first problems that we ran into is, if a broker fails, you have to generate this JSON file to choose. Like again, if you have partitions that don't have a replica assigned to them. So for instance, if you recall the last screen, say 1001 failed, every single partition would have a hole where 1001 was. And the original intent of Topic Mapper is to generate those partition maps without moving other partitions. We found that using the out-of-the-box tools would let you build repair maps, but then it might cause things to move where you didn't anticipate. And so Topic Mapper is originally built for that, but now it's kind of at the core of all of our partition placement among all of our Kafka brokers. And some of the goals of it, it aims to maximize the partition leadership across brokers. And then it also aims to maximize the replica sharing among brokers. There's a lot of distribution that we want. We want this data just really well spread out. And then another goal is also isolating replicas by locality. What that means is essentially honoring the rack awareness. So we don't want any 2 replicas placed in the same availability zone. And I think one of the biggest features here is that we can choose whether partitions are placed on brokers by simple counts, which was the original design of this. And later, I included storage balance, which I think was one of the most powerful things that we gained by building this tooling in-house. So every single day, we're using it again for partition of broker mappings. So that could be if we create a brand new topic, choosing specifically which brokers partitions for those topics go to. Failed broker replacements. So this is something routinely that we're doing pretty much every single day. Again, similar to the out of box tooling, except that this gives us some more granular controls. And then the storage-based cluster rebalancing, I think, has just become really core to what we're doing here. The out-of-the-box tools don't really give you controls to really think about storage, and this is one of the big features here. Yeah, and so this is one of the examples. You can imagine like a set of brokers that over time, storage utilization across those brokers might drift. And so what Topic Mapper does is it's using metrics to inspect things like partition sizes, broker storage utilization, and come up with a rack-aware assignment map so that you essentially generate a file that you would apply using reassign partitions, which is an out-of-the-box tool. And once it's done being reapplied, you can see that the storage utilization among the brokers is brought closer in line with one another. When we do this, every single time that you apply a map, whether it's for replacing a broker, bringing storage balance into check, it counts as a broker reassignment. And when you do reassignments in Kafka, you can set a static throttle rate. You can say reassign this data at 20 megabytes per second, 30 megabytes per second. One thing we found is that we were doing this so often that we couldn't just simply set static rates. The idea is that we wanted to actually run these replications as fast as possible without impacting consumer traffic. And so I wrote an additional service called Autothrottle that's similar to what Topic Mapper is doing. It's looking at metrics, but it's doing this on an ongoing basis and constantly adjusting the throttle for you. And this is what an internal dashboard might look like using the Autothrottle service. On the upper left graph, you can see the under-replicated partition count. This could have been, repair. More realistically, it was probably a rebalance. And every single one of those bars actually denotes like an autothrottle event. It could be something like a new throttle rate determined. And so what it's doing is every single check interval, it's looking at the real-time broker network throughput, and it's making a decision. let's say that consumer traffic maybe starts dipping, midway through your recovery. Autothrottle can see that, okay, there's more bandwidth for replication. Let's turn the throttle up, and vice versa. You might have consumers that were turned on halfway through the replication. You might want to actually start backing off the throttle. And so this is all powered with a pluggable metrics backend. So it's not Datadog specific. Anytime you're using topic mapper for doing storage rebalancing, it's actually reading that data right now. It reads it directly out of Zookeeper, and it's stored in Zookeeper with a tool, just using some JSON formatted metrics data. And so you could really back this with any metric system you want. I've seen some cool open source tools that the community has made so that they can support it on systems maybe outside of Datadog and benefit from everything we've done here. And so one of the things that is also core to our scaling operations is that we have this concept of maps or pools, and pools are subsets of brokers that we bind particular topics to. And this is one of the reasons that we've created our entire ecosystem of tooling, is that we wanted granular control of what data is where, and it gives us pretty easy way to do things like isolate workloads or maybe put workloads on resource optimal hardware. You might find that one workload might benefit from larger but slower hardware, and another one might benefit from lower latency and faster, possibly more expensive hardware. And yeah, by breaking things into these separate maps and pools, it gives us that level of control. And something I've written about in the Kafka-kit open sourcing blog post is that we actually think about all these different pools as their own separate capacity units. So in a cluster that might have these two maps, the capacity, the throughput, the latency of map 1 has no bearing on map 2, and we can kind of treat those independently.
All right, next let's talk about Kafka and Kubernetes. And I think for me personally, this was a little bit weird. So for anybody not familiar with Kubernetes, Kubernetes has its own key value system called etcd. And looking at it, it seemed a little bit confusing. Maybe Balthazar, you can shine a little bit of light on why we have 2 key value stores?
Because why not, right? But more realistically, the reason why there's 2 different key value stores there is that Kafka is an Apache project that was an ideal fit, for Zookeeper. Well, I guess Zookeeper was an ideal fit for Kafka because they both belong to the Apache Foundation, and getting distributed agreement between systems is really hard. Zookeeper has been really solid and for a number of years, but I think it's a little rough around the edges when it comes to operations. Backing up the data, restoring the data is kind of a challenge with Zookeeper. And I think I think Kubernetes, by creating etcd or using etcd, wanted these features relying around operations. So here we are, ended up with a ton of distributed system. But if you think about it, if you run Kubernetes on, say, AWS, and you run Kafka on top of it, you also run Kubernetes on top of etcd, which is running on top of a virtualized hardware, on a virtualized network, on a virtualized environment, on a, like it's turtles all the way down, which makes it super confusing. But if you forget about all that, then it's working really well.
All right, now that being said, we should probably introduce who you are. So you want to introduce yourself?
Sure. So my name is Balthazar Rouberol. If you try to pronounce it in English, it breaks. And so I've been working at Datadog for the past 3 years, and I'm the team lead of the data infrastructure, the data reliability infrastructure team. So we focus on how to deploy, manage, monitor, operate data stores in and out containers, basically. So trying to describe how we deploy data stores in Kubernetes, we have to answer one question first, is why? Like, what does that give us? And if you read Hacker News, or if you read anything out there on the internet, the general sense of agreement is that it's a really bad idea. And so it's an interesting question. Why do we do it in the first place? The reason why we do this is that we're actually a multi-cloud company, and it gives us a canonical, kind of unique way of deploying something on different cloud providers. That being said, it is a hard thing to do because Kubernetes by itself, works by scheduling resources on a pool of resources, scheduling applications on a pool of resources, and you don't have a fine control on where you deploy. And so it's kind of a weird thing if you think about, this kind of fuzzy scheduling, I don't know where I run versus I need to have data. So the thing that we've come up with at Datadog is a custom Kubernetes resource that we call the node group. It's a logical representation of you asking for compute resource. So when you say, hey, I want a node group of size 3, the controller, a piece of program running in Kubernetes behind it, will basically go and talk to the cloud provider API and provide you with a set of autoscaling groups if you run in AWS, or a set of managed instance groups if you run in GCP, or scaling groups if you run in Azure. The point is, it allows you to request dedicated resources. And so we break away with the way Kubernetes was designed or intended to be used in the first place, because we use it as a scheduling system on our resources versus on a pool of resources that we don't really control. And so this is the general strategy of us deploying data stores on this thing. And so while node groups are actually a custom resource, what we do after that is fairly standard. We use what I call a stateful set, which is a resource that then is responsible for the creation and lifecycle management of what is called a pod. And a pod is one or more containers running in the same namespace. So for Kafka, we just have the one container, which is Kafka, unsurprisingly. And so the stateful set here is just responsible for the creation of Kafka. And we do it in a way that we create all the pods in parallel. We have a predictable scheme to assign a Kafka Broker ID with giving a pod name. And so we're allowing ourselves to start all the pods in parallel. So for us, it is actually as fast or as slow to create a 3-node cluster or a 300-node cluster. It just takes a constant time.
Nice. Sounds useful.
It really is, especially if you have to provision a cluster in a hurry, if you want to do a failover because something has catastrophically broken or something like this.
So let's talk about disk store. How does that work?
Right. So remember when I said that running things on Kubernetes when you have data is a really bad idea? It really is if you don't know how to manage your data, right? So the idea for us is we need to maintain two properties. We need to have persistent storage, and we need the data to be there. And so what we've chosen to do, we were doing this even before we were running at Kubernetes, is use local storage. We're using SSDs, NVMe to be precise. And so we are still doing this in Kubernetes. The way that we do this is we provision through node groups instances that have local data, local storage, by choosing instance types such as i3 or i3ens or things like this. When the node group creates the instances, what happens is that these instances have local disk, and these local disks will be represented in Kubernetes by a resource called a PV, a persistent volume. And so that just describes the amount of space available, the type of storage, so in our case, it's local storage. And then when we want to schedule Kafka on that node, the scheduler will put it there and will associate the pod with the volume with a claim. So that means that no other pod can claim that disk. So no other Kafka pod can just come along and write to that disk as well. And so we avoid data corruption, data shadowing kind of thing happening there. And it also means that if you kill that pod, because maybe you're just doing a rolling restart or something like this, it will just still through the chain of PVC PV node be rescheduled on the same node. So this way you're making sure that it restarts on the same node with the same data. And so you have a scheduling system that is a little bit more predictable than just schedule something somewhere. So yeah, so this is kind of the properties that I talked about. We are using local instance store drives. The data is persistent between pod restarts, which is super important because you want this to happen, to have reliable data storage. The data is, and this is where it gets interesting, I think, because the way you schedule things and the way you configure things have a direct impact on operations. What used to happen for us is every instance that died would then page someone down the road because we needed to use topic mapper to reassign data to the new node that just appeared. We're going to detail exactly how things work afterwards, but what I can tell you right now is that the data right now is streamed to any new replacement node fully automatically, and that's involving the kind of predictable broker ID scheme that we have. And one thing that is very important in Kubernetes, and actually not that easy, is to inform the pod of exactly where it's running in terms of availability zone, because you want to maintain that property that Jamie talked about, where the brokers themselves are aware in which rack, in which zone they run, so that Kafka can make sure that the different partitions, or topic mapper can make sure that the different partitions run in different, the different partition replicas, run in different zones. Otherwise, if you lose a zone because something happens at the cloud provider level, you lose all your data, which is kind of not the point. So the way that this happens conceptually is that you inject that information, the zone that you can query from the Kubernetes API, or in our case, it's actually injected by our tooling automatically at the Kubernetes level. So we just have that information at the ready, and we just pass it along to the Kafka properties file through the broker.rack configuration entry. Something that is interesting there was the notion of broker identity, because again, the way you deploy things has a direct impact on operations. It also has a direct impact on monitoring. So what we wanted to do, we wanted to be able to match node level or system level metrics, such as disk usage or disk latency, network throughput, something like this. And we wanted to match that with Kafka metrics, such as, I don't know, number of under-replicated partitions, or a number of threads being busy, or things like this at the application level. And to be able to do this in Datadog, you need to have a common attribute between the node, the instance, and the Kafka broker. And so that's the broker ID, basically. This allows us to pivot between the node, the instance level metrics and the application level metrics. The way we do it is really simple. So this is kind of what we used to do. So the doodle is a little bit out of date, but no worries. What we do is, we used to query Zookeeper for broker ID, and now we do something that's a little bit smarter, I think. We just have, like I mentioned, a predictable broker ID scheme that just takes the pod number. So if you have a pod number running on node whatever, and you lose that node, and it's rescheduled on a new replacement node, you keep the same broker ID. And this is really kind of key to both having a stable monitoring system and stable metrics, but also by doing this, you get auto repair for free, because when Kafka is rescheduled on a new empty machine with the same broker ID, the partition assignment just stays the same, and Kafka just catches up automatically. So you get that for free, just by thinking about how you schedule a system. Now, we've mentioned, running data store on Kubernetes is a terrible idea if you don't think about it. So let me just insist on this, because it's kind of key. So one thing that we do to kind of get predictable performance out of the machines that we have is we only run the Kafka pod on that machine, plus a couple of utility pods that we have, like the Datadog agent or things like this. We run one Kafka pod per machine, and we make sure that we get the same number of pods per zone. This way, we can actually get partition assignment that is as sane as possible using topic mapper that respects the rack. Because if you have one pod in zone A and 3 pod in zone B and 6 pod in zone C, the partition assignment, if it's trying to respect constraints, will get a hard time to get it right. So this is kind of one key feature of our deployments. Where things get, I think, really interesting is when we tie all of what I've said, node group, stateful set, etc., to topic mapper or Kafka-kit, which is really kind of the foundation layer of our operations. We've mentioned the notion of maps and the notion of pool, the ability to isolate topics on a subset of machines in the cluster. So if we look at Kubernetes, we're doing this by having a separate node group and stateful set per map. So in the case of that example that we gave you, map 1 was just every topic starting with events dot, We have a specific node group that provisions specific machines on which our specific stateful set will just provision Kafka on these and on these only. And on these machines, on these workers, we have all of the events.something topics. And we do the same for the other map in this way. And we also do it when we create the topics. We don't do it afterwards, so that if we forget, we might have topics kind of all over. When we create those topics, we pre-assign them to the appropriate machines. So we are always sure that there is no topic overlap on different node groups, which is really important in a case of a rolling restart. And so to get a rolling restart right, you first need to be able to answer the question of health and readiness. So in the case of Kubernetes, you have two different what we call probes. You have the readiness probe and you have the liveness probe. If you fail a liveness probe, Kubernetes will restart your container. It means that you're not running. If you fail the readiness probe, it means that someone trying to resolve your service DNS will not see you, meaning that, in other words, Kubernetes will not send traffic to you until you are ready. So for Zookeeper, it's pretty easy in terms of liveness, is the port open? But for readiness, I've seen something be done over and over and over and over, is using the "Are you okay" API call for Zookeeper. And if you look at how this is implemented, the handler is just responding, yes. Whatever happens, the world could be on fire, Zookeeper would be saying, I'm okay. So it's very nice of him, but it's actually not telling you much. It's no additional information, I guess, than is the port open. So what we're doing is that we're using the SRVR, I think, API call, and we're looking at the mode of the cluster. Am I a leader or am I a follower? If you're not any of these things, you're not ready. And that has worked remarkably well. When it comes to Kafka, for liveness, we're doing the same thing. Is the port open? For readiness, remember how I mentioned rolling restart? Rolling restart is actually gated before you kill one pod and you let it go back up, and then the next pod will only be killed if the previous one is ready. And so that is kind of key to orchestrating a sane rolling restart. And for us, what that means is we have a special probe that checks if Kafka has 100% of this partition fully in sync. And so by adding a little bit of delay between two restarts, you can actually have a pretty sane rolling restart happening by just having these conditions met. What I need to mention before we kind of show you a picture of what a rolling restart looks like is that all that is really nice until everything breaks. And when you have a compound, like a set of incidents, and you have interdependencies between your data, and sometimes basically the stateful set will try to restart things in order, you need a way to break away sometimes from these conditions and just force something to be ready to break away from that interdependencies, from that chicken and egg situation. So what we do is super simple, super crude, super hacky, but it works well. Our readiness probe has this precondition. If there is a certain file found on a file system, it assumes that everything is ready. And so that allows us to have a break the glass command that would just touch that file on the container. And while that file is there, the container is considered to be ready. So it could be completely broken, but by forcing Kubernetes to assume it's ready, we can then have other pods be rescheduled and overall the data source be repaired. It's kind of a nice trick to have. So rolling restarts, so what we're looking at here is the number of under-replicated partitions. We have 3 time series, 3 colors, 1 yellow, 1 orange, and 1 red, which is, in that case, 3 stateful sets. And what you're seeing is that the number go up, and then it goes back down again. And you see that a couple of seconds after that, it goes up again. So that means that basically one one Kafka brokers go down, it restarts. So you see the number of under-replicated partitions catch up, and only when it's down to 0 can the next pod can be restarted again. What you see though here is all of the stateful sets restart in parallel, and that's doable because you don't have any topic overlap. If you do that and you have topics all over, you will maybe at some point have an offline partition. But because we ensure that the topics are created on different maps, there is never any topic overlap, and we can basically restart as fast as possible by restarting everything in parallel while still being safe, because we only restart one pod after the other per stateful set.
Next, let's talk about operations. And I know you guys have been working on something where you're doing automatic node replacement. What does that look like, and what does that mean?
What used to happen in the past, like I mentioned, is imagine you have a Kafka cluster where you have broker ID 1, 2, and 3. The machine that hosts the Kafka broker 2 fails. It's completely broken, kernel panic, something, or the disk is dead or something like this. You provision a new one, and in our previous system, that new replacement machine would then have Kafka be scheduled on it, and it would get an incremental broker ID. So it would get broker ID 4. At that point, we would need to have topic mapper run to automatically figure out that 2 was gone and 4 was the replacement, and then we would need to stream data. And so in terms of pager, someone would get page at that point, would have to go through that sequence of events, run the topic mapper command, and have the data streamed. The way that we do here, I've mentioned it, we have this stable broker ID scheme where the pod is rescheduled on that new machine, but still has broker ID 2. And so that makes sure that whenever this pod is scheduled, it will catch up fully automatically. And so we have adjusted our monitoring scheme and how we, our monitoring system, I guess, and what metrics we monitor on to tolerate some under-replicated partition. And if you have under-replicating partition for too long, that maybe the node replacement has somehow failed and a human being needs to go and have a look. But that has reduced the amount of pages that we get dramatically, thus allowing us to have more brokers and to scale Kafka even more at the scale of the whole company.
Nice, makes sense. All right, how do we ensure that that node replacement doesn't harm live traffic?
Yeah, so if you recall the Autothrottle tool that was mentioned near the beginning, this is also used for recovery traffic as well. So the original use of that was kind of anticipated reassignments. So, the most common use case would be storage rebalancing a cluster. We compute a storage, balance map, we apply it, and then we throttle replication traffic there. One thing that was different in this automatic node replacement here is that since it's kind of hinged on just reusing IDs and making sure you're reusing them in the right place, there essentially is no reassignment there. Brokers come online and they just start replicating from the beginning of the leader replica, like right at the head of the log. And because there is no reassignment happening, Autothrottle doesn't really see an event. And so I recently wrote support where you can kind of out of band, just apply throttles to brokers. And so what we do is that when a replacement broker comes up, it essentially tags itself in Autothrottle. I'm a replacement broker, let's throttle my traffic. And it kind of works in the same fashion as from that point as it would for a typical reassignment.
How do we reduce the likelihood of data or bandwidth hotspots in general?
I could take that one as well. Yeah, and so this is actually one of the big motivators for doing storage balancing in Kafka. And so if you take a given topic and you look at the partitions for a given retention period, you'll find the partition size is fairly well coupled to bandwidth. There's just some simple math there, right? It's the size of the partition is literally the amount of data you're sending in and how long you're holding on to it. And so by doing these routine storage rebalances, you're also rebalancing bandwidth. Again, if you also recall, some of the objectives of Topic Mapper is also things not just even storage utilization, but good distribution of replicas among brokers, even partition leadership distribution. All those are also those heavily influence bandwidth, both in just ongoing operations, so normal producer and consumer traffic, and along with recoveries. And so individually, having even leadership distribution means that as you're reading and writing data, assuming that your storage balanced, you get pretty even throughput in the network. And then having maximum replica dispersion among all the brokers means that if a broker fails and you replace it, it's pulling in from as many diverse sources as possible, which means that you avoid too much impact on any one broker.
Gotcha. Sounds like ideally it never becomes a problem.
Yeah, it's a goal.
Okay.
If I may just Oh,
Yep.
sorry, Kirk. If I may just ask, let me just act like you just for a second to asking a question to Jamie. But say, Jamie, how do you handle the case of you have to do Kafka is only able to handle one reassignment at a time?
Yeah, so there's this issue right now. Kafka can only handle one reassignment at a time. We found this actually kind of influences our ideal maximum cluster size. I actually want to go back to the beginning of the slide. You don't have to actually go back to the beginning, but I'm just reciting some stats we gave. We mentioned having double-digit gigabytes per second, hundreds of gigabits, petabytes of storage, and we said tens of clusters. Part of the reason that's only in tens of clusters, originally, before Kubernetes, it was not so easy to bring up and manage increasingly large amounts of clusters. And one thing we found is that as the cluster size goes up, the likelihood that you're going to have, the need for multiple recoveries at once, just kind of increases. And so there's a couple different ways of going around that. One is simply more clusters for, the size of your total workloads, which Kubernetes helps us there. Another thing that I'm working on is that even for a given cluster, you might find yourself in a scenario that a broker fails, somebody replaces it, or they're doing, a storage rebalance. That's an ongoing reassignment. Before that finishes, you might find, okay, we have another scenario that kind of demands this as well. And so one of the services I'm working on is essentially a priority queue for just enqueuing these reassignment jobs. And there's a lot of cool logic that we want to put in place there. We could do things like automatically chunk or merge reassignment jobs. So let's say that we have 3 different rebalance jobs to go. These could get enqueued in this system, and it might say, hey, each of these rebalance jobs, it's only moving a couple terabytes of data. Let's just merge these all together into one job and get it done in parallel. And kind of in contrast to that, you might do a really big reassignment job and it says hey, this cluster grows, at a slow rate. You're about to reassign, 400 partitions. Let's maybe chunk this into a series of steps. And so I'm not sure if that's the idea you're getting at there, Balthazar, but
exactly what I was getting at.
Yeah,
Nice.
and kind of the long game of this though is if you actually had a nice diagram of all these tools, we have higher leverage of doing operations per cluster, and we want to make all of these really common operations increasingly hands off, so that clusters get closer to a point of kind of self-managing, and then it's the human's job to stop doing so much operations and kind of focus on just the software that manages the clusters, and also, just the underlying infrastructure. We kind of want to just start thinking of these as just large pools of resources and stop thinking so much about specific clusters or specific operations that need to happen.
Let's wrap it up. And I know we have at least one question from the audience. So to conclude, we twist the Kubernetes model to ensure we have dedicated resources. We take advantage of Kubernetes APIs to simplify configuration. Kafka-kit works well in Kubernetes. And we're trying to get to the point where we are automating operations everywhere, where it makes sense and where it's possible.
The reason why we say that it works well is that it doesn't make any assumption where you run your software.
Yeah.
So it just
it works well for at least 2 models.
Yeah, and that was one of the the design objectives of it, is that we started small. We solved problems that we had when we were at a fraction of the scale, and we incrementally just kept adding to it and kind of built this ecosystem of management that was generic enough too that we could adapt it to things that we didn't anticipate, like entire infrastructure migrations to new infrastructure management, maybe new cloud vendors, things like that. Somebody said they may have missed it, but are you using an embedded Zookeeper or a separate Zookeeper cluster alongside Kafka?
Let me actually answer. So Jan has answered. Jan is in the audience since he's also working in the DRE team. So we don't have fans in the audience that know exactly how we do things. But yeah, every time we deploy a Kafka cluster, it has its dedicated Zookeeper cluster. And I know there's a kit out there to get rid of Zookeeper and replace it with Raft consensus between the Kafka brokers, which I think is really exciting. Our tooling actually stores data into Zookeeper, so we can think about reducing the amount of Zookeeper machines we deploy, maybe by having a centralized Zookeeper with every single metadata from all clusters, or we could keep doing this. Right now, I think this works really well. Zookeeper is the least of our problems so far now.
Yeah, I would add to that as well. I mean, I hear that a lot. People saying Kafka's great, but it's hinged on Zookeeper. Zookeeper's kind of terrible. Totally understandable. I mean, if you ever have to repair Zookeeper in a production incident, it's not the easiest. But I think if you have a good setup, I think we do. It's pretty low maintenance. And as far as having a separate Zookeeper cluster, in my opinion, it's a pretty small expense for relative to the total Kafka clusters are running or total Kafka brokers, I guess. Having a 3 to 5 node Zookeeper ensemble is just a really easy availability guarantee. Just isolate everything. It's I think about it a little bit more. So in some of our environments where we might have a bunch of testing clusters where there's only like 3 to 5 Kafka brokers, then you start thinking like, hey, do we really need 3 Zookeeper clusters? Or I'm sorry, 3 Zookeeper nodes per cluster. But again, that's some cool things you could do with Kubernetes. Like that's maybe a scenario that it's useful to then bin pack resources. I could see in a testing environment, like you don't need that full isolation where there's a one-to-one mapping of cluster machines such as Zookeeper or Kafka to real underlying EC2 machines or whatever your instance type is.
Gotcha. We also have one more question that came in through the question and answer form. Do you use pod disruption budgets to minimize disruption too?
Yes, we do. So kind of backing up on if you remember that scheme where we have 2 node groups, 2 stateful set, and different topics assigned to the machines, we actually have a pod disruption budget of a max and available broker, max and available pod set to 1 per pool or stateful set. So we do this for 2 reasons. We have a bunch of tools in the Datadog Kubernetes ecosystem that will proactively reboot nodes if they want to do a kernel upgrade, if you want to patch a vulnerability or something like this. And these tools will respect the pod disruption budgets that we advertise. And because we don't have any topic overlap between different stateful sets, then we could say we're okay with proactively cutting ourselves away from 1 broker per stateful set. We don't want more than that. Just because we're playing conservative, we could, but this is like the safe option. Going slow, but going fair. And this is where the readiness probe actually makes sense, because you can only move on to the next one when the previous one is fully caught up. So by doing this, you're kind of really safe while playing nice with the teams that maintain that Kubernetes ecosystem for us.
This is a question from me. How do we handle upgrades for Kafka in general?
Either you do it, you have like a minor patch. What we do is we just deploy, we build a new image with that patch installed, and we just deploy that cluster with that new image. And Kubernetes will take care of doing the rolling upgrade of the cluster. So we will do it on a stateful set basis, 1 pod after the other, and that will be gated by the readiness probe I keep talking about. And if we do a major upgrade, like we've upgraded in clusters like 0.10 to 2 something, then we tend to have the approach of looking at it as a blue-green software engineering project, right? Or practice, where we deploy a second fully separated cluster using the new version that we want to run on. And we dual write to both the clusters, or we migrate over the consumers and producers over time, and we make sure that there's no performance regression. And if there are, we actually investigate. If it's anything more than a patch release, we might go through that effort. And we have canonical version that we guarantee we know how to work with. It's like the devil you know versus the devil you don't. And so we tend to be kind of conservative about the versions that we allow. But when it comes to patch versions, we tend to be kind of okay with releasing.
Gotcha.
Yeah. One thing I'll actually add to that as well is that with the major versions, there's a big bit of the client interaction with the cluster as well. It's pretty important. We find that it's kind of the blue-green pattern kind of just makes sense anyway, because when we're doing these major version jumps, it probably means pretty major version jumps for the clients as well. There's lots of different features, bugs, hopefully solved, probably new bugs introduced, things like that. And so we kind of like to do it as just like one big group, right? Like get a new cluster up, get an entire pool of producers and consumers, and and start shipping over increasingly large amounts of traffic and, observe it, all the normal, progressive rollout stuff, and kind of make sure that everything is okay before you ultimately cut over and kind of just sever off the old cluster. And so a lot of our infrastructure is kind of grown that way of a continual, addition and deprecation.
Which is something that we're also working on fully automating step by step, so that we don't need to have humans as involved as we need to have today.
Gotcha. And that's a perfect segue to my next question. What are the remaining manual pieces?
It's kind of giving away the crown jewels there.
Yeah, storage rebalancing is a frequent one. So a lot of what I'm working on right now is getting storage rebalancing completely hands off. Again, the way I talked about how we approached the tooling was incremental. We started with solving small problems first, but everything that was built with the idea in mind that eventually it'll start being operated by humans, but eventually it's going to be part of a big single machine that's mostly computer operated, right? And so if you look at tools like Topic Mapper, where you can compute the storage rebalance map. When you apply it, Autothrottle is making sure things run as fast as possible without breaking things. And then I talked about another component where we can then start enqueuing maps that get run automatically. Like, again, another service will determine when is best to run those, how, what way is best to run them, whether jobs should be joined or broken. And then kind of the final step to that now is adding software that kind of orchestrates all those decisions. It'll look at a cluster and see something like, utilization hotspots, and kind of incorporate all these other factors and make a decision. It'll say, okay, I see that this map is completely out of balance. Let's do a topic mapper rebalance, enqueue it, that gets applied, Autothrottle, paces it. And then, the final step after that, hopefully something we're talking about another year from now, is, auto scaling. You take all of those mechanisms, and now if you see, maps on the verge of capacity exhaustion, we could do things with Kubernetes like resize the auto scaling groups that we've abstracted through the Kubernetes API, increase resources, and then again run scale up operation completely hands off. And I think that's one of the ultimate things that we need to get in place to just manage increasingly large numbers of clusters, which is the trajectory Datadog is on. That
makes a lot of sense. I heard schedule and I immediately thought we're making Kubernetes all over again.
No, we're there's a lot that it brings to us that we'll happily not create on our own. And a lot of what we're building, in Kafka is models that you can find in other software that I guess just didn't come out of the box with Kafka. And understandably, it's focused on doing particular things very well, and it served us well. And so we're kind of filling in those gaps, particular to our needs.
So I don't know if you want to answer this one or not, but what do we do if we know we're going to get a huge bunch of traffic? Is there something we have in place to handle known incoming large-scale events that are going to happen?
Yeah, so in that case, we just do preemptive scale-ups. Like if we have a pretty good idea of how much we're talking about in terms of additional data, then we're looking at the available capacity and we adjust beforehand. And if it's something that comes of a new customer that we know we're going to onboard on that date, we actually have we get a ticket or something like this where we know we have that amount of time to do it. And obviously if some things don't go according to plan, if they have more or less capacity, then we adjust afterwards. Using topic mapper rebalances or something like this, where you can scale up or scale down the number of pools you want to assign partitions to, and then you just have to garbage collect the empty instances.
Yeah, and another thing on that as well is that there's kind of two types of workload growths that I think of offhand. One of them is kind of the surprise, right? It's some workload just increased by 10 gigabytes per second, which is, absolutely happened. And those ones, you kind of handle it on a more ad hoc fashion. It's like, okay, this is happening now. Let's use the tooling we have. We could usually respond to it fairly quickly. There's also the organic growth. So just the steady upwards growth of a given data set. And those are really easy to handle. So one thing that's really essential to our ongoing operations, absolutely not to pitch Datadog, but it's Datadog itself. So we're using, forecast monitors and all these other things to kind of just anticipate when natural growth is going to push something into like the scaling territory. We kind of have all these bands that kind of tell you the overall health of the clusters and where capacity is. Yeah, and it just makes it a lot easier to manage.
Something that we do as well is, especially during the weekends where you might not want to get paged for like capacity issues, we have something that just runs alongside the cluster, and we'll see what's the minimum absolute retention you cannot go beneath with, and we'll adjust the retention by like maximum of 15%. To see if you could just go without getting paid during the weekend, and then you'll get a low priority page saying, we slightly adjusted the retention for that topic. You might need to get, on Monday to do a small upscale or something like this. But instead of just having human being do the work, maybe adjust slightly by removing some data during the weekend or something like this. And we have another strategy that when you get another topic, like a new topic, and you don't exactly know how much data is going to be pouring in, you might want to say something in the vein of, this is a really new topic, so we're just going to keep the retention arbitrarily low, so we get a couple of hours to assess if our scaling was right. And so if it wasn't, we can adjust before it actually blows up and fills all the machines.
Yeah, that sounds like a good approach.
The second half of this double episode is going to start in just about 5 minutes, which is Datadog on Kubernetes. But that said, another great question came in here. So I'm going to jump into the intro for Datadog for Kubernetes. Thanks on my behalf for joining. I'm sure Kirk will have a farewell message after this is over, but don't want to interrupt. And if you have additional questions aside from the one that came in, this Zoom will stay open as long as you all want to chat. So enjoy, and thanks for attending Datadog on Kafka.
One more addition to the, handling the kind of explosive growth scenario. So if you go back to our model of having these pools, one thing that we do is that we tend to set kind of an upper size on pools. Like let's say it's 32 brokers or 64 brokers or something like that. And we'll kind of just storage bin pack topics into these pools. And by doing that, by combining a lot of varied workloads, it's just a lot easier to kind of run things right within our capacity targets. And so let's say that within a shared pool, a single topic just starts blowing up capacity. One of the tricks we have is because of the abstraction of backing pools with auto-scaling groups, we can simply just fire up a whole entirely new pool for a hot topic and back it with say 12, 24, just whatever number of machines it needs. And in our configuration, you just pluck that topic from that pool and stick it into its own dedicated pool. And then using all the tooling we've described through this talk, just pushing that topic over live, and then it's got as much headroom as it needs.
Let's answer this question. How do you budget topics versus cluster size? Are you hard limiting message length, or just getting rid of things, or are you hitting a certain retention?
Actually, whoever asked this, feel free to add more to it if this wasn't answered, directly. But we don't particularly set topic budgets. So when people turn up new workloads, by people we mean other developer teams that we're serving. If it's a small topic, we kind of don't really think about it. People just create things as they need it, and we'll add it to the shared pools, and we kind of monitor the overall usage, right? We can say that this team is using X number of terabytes of data, or X amount of throughput, and it costs some value, and it's kind of up to them to determine things like retention, replication factor, all of that. The time that our team cares the most is if somebody and this happens often, somebody turns on a new workload, and the real world throughput was some multiple above their estimations. Then we do put some controls in place. We might say things like, you've spec this at replication factor 3 and it's 72-hour retention. The workload's exploded and we can't keep up with the growth of it. Can we trim this down to 48 hours or 36 hours? And something Balthazar mentioned too is that we have a programmatic way of doing this as well. It's not completely in use, but the idea here is that you can kind of set like target retentions for topics, but also minimums. And so say your target retention is 72 hours. So in our capacity model, we'll make sure that there's enough capacity for it. But if the floor retention is say 48 hours, say that it's desirable for this topic to hold 72 hours worth of data, but it's okay if it goes down to 48 hours. If they massively outgrow their intended capacity targets, then the system just trims them back down to the floor. And the nice thing is that if you have a floor set, like a reasonable one for all the topics in the pool, it can kind of just crawl through the topics and take off a safe amount and make sure that everything kind of stays in check. Meanwhile, a human is usually assessing and adjusting capacity.
Thank you so much, everybody, for joining. Thank you, Balthazar. Thank you, Jamie. Appreciate the time. This was great. Everybody enjoy the rest of your day.